lost along the way, so I want to see if we can avoid that. All right, so you put the data in, in your home, you go to statistics. We're going to type in the X values and the F values here, so 14 through 24 even. So if you just picked up a calculator, again, you're going into statistics, and you're typing in the data to value V1 and frequency. Okay, so I'll give you a couple seconds to do that. So we're hitting statistics. And under data, you're putting in the values into V1 and frequency. Who are we missing? Here. All right, so once you have all those values in, you're going to go to stats, and you're going to scroll down. You're going to find the sample mean and sample standard deviation. So you need X bar and S. All right, so all this stuff here came from statistics, followed by data. Now it's statistics, followed by stats. All right, so right at the top line there, just going right over to stats, hit OK. And when you run down the list here, eventually you should come across, I have stuff in another list, so we'll just ignore that for now. You should have a sample mean and sample standard deviation. All right, X bar, X with a little bar over it, very creatively known as X bar, and S. All right, so we're looking at 18.829 and 2.144. All right, we have to do a series of computations here to determine whether this data set is considered to be a normal distribution. All right. And so that comes from this 68, 95, 99.7 process. All right. So what we do is we compute X bar minus 1S, X bar plus 1S. All right. Once we do that, we compute X bar minus 2S, X bar plus 2S. And the last interval will have 3s instead of 2s. All right. Sort of exaggerating how I make my S's, just to make it clear that these aren't 5s. Down the line, it happens in every class. Right before a test or when you're working on an activity, somebody will say, I understand everything, I don't know where the 25, the 15, 25, and 35s came from. All right, so make sure that your S's look like S's. All right, now, what I would want to do is pull this information from this output screen and bring it into my home screen so I can do the computations. All right. there is a copy paste function. So what I would do is hit, well, unfortunately you got to do it one at a time. You can't like, oh, actually I never even thought to try that. Well, you can't copy multiple items at the same time. All right, but I'm gonna make sure I'm not lying here real quick. Yeah, you can't do more than one at a time. So what I'm gonna do is I'm gonna go right onto that 18.82927 and hit Shift var. So Shift var. It's 2 to the left of the clear button. It's right next to the toolbox, basically. Superhearing. Yeah, so Shift var, and then go back into your home screen. So hit home, go to calculation, and then Shift toolbox. Except my screen is kind of funky. I'm sure it's working for you perfectly fine. Come on, I got it with this app. I got to hit it precisely the right way, otherwise it doesn't come up. There it is. Okay, that's not the right number. I must not have copied it correctly. So, Shift var, Shift. There it is. Yeah, like I said, on yours, it probably worked first time, no problem. But with the touchscreen, it's so weird. It doesn't recognize what I'm asking it to recognize. Anyway, Shift var to copy. Shift toolbox to paste. Now you might look at this and say, well, I could have just typed it. Like, why did I have to do all this? Well, sometimes the decimal values are so crazy that you want to just copy it, especially if scientific notation gets involved. All right, so there, maybe not for this instance, but there will be an instance where you would want that function to work. All right, so then I'm going to work on this first computation here, x bar minus 1s. So I'm going to type in minus 1 times, now I just need the s value. All right, so I'm going to go back into the stat editor, statistics. I'm going to grab the standard deviation, Shift var to copy, Shift toolbox to paste. That time it worked on the first shot, I don't know. All right, you get it in there the right way the first time, every other computation is going to be very easy. All right, because all it is minor edits here and there. All right, so I hit OK or I hit Enter, and it gives me 16.68. If we're rounding correctly, 686. So that's our first computation. So then what I'll do is go back up to that, hit OK, so up arrow a couple times, right onto the same expression, and just go back and change that 1 to a 2. So we're going to get all of our low bounds here first, and then we'll get our high bounds. 14.542. Up, and away. 2 gets changed to a 3. My low bound for the third interval is 12.398. And we're just going to do the same thing again, changing all the minuses to pluses. All right. So I'll go right up to the top one, hit OK, brings it down to the bottom of the screen, minus becomes a plus. So my upper bound for my first interval is 20.973. make the edit. 1 becomes a 2. 23.117. 2 becomes a 3. 25.260. So those are our 3 intervals. It's all just computation, but it's a little bit more user-friendly if you use the copy-paste function, in my opinion. All right. So now what we need to do is figure out how many values fall between this number on the low end, the 16.686, and the other number. I'll get my pointer out here. This other number here, 20.973. So I look at the data set, just only at the x values here. So I'm only looking in this area here. I'm looking to see what, if any, values will fall in between this number and this number. All right. So I'm essentially asking myself, one at a time, does the 14 fall in that interval? Yes or no? Does the 16? Yes or no? And so on. All right. But really what we're getting at here, and you don't have to draw this, but I'm just doing it for demonstration purposes. So we have, let's say, 15, 16, 17, 18, 19, 20, and 21. This list of integer values goes on forever. Right? All I'm asking myself is, where would the 16.686 get plotted on this number line? So probably somewhere around here. And where does the 20.973 get plotted? That would be over here. All right. So I would only want values that fall between these two numbers, the 16.686 and 20.973. So looking at my list, I would just say, okay, well, I'm looking at numbers really from 17 to 20 because they're all whole numbers. If the number that I'm given is not between 17 and 20, I'm going to disregard it. All right, inclusive. So 14's out, 16's out, 18 works, 20 works, 22 is too high, that would be added off the number line. And so therefore 24 would be too high. Remember, the frequencies are just telling you how many times each number happens. All right, so if I wanted to find out how many numbers there were in the set, I would just add it up. So 8, 22, 35, 40, 41. So number of values in the set. Just did a quick double check on that. All right. So of those 41 values, 27 of them would be in the interval that I'm looking at. All right. So I'm looking at 27 values in the interval. '41 values in the set. So I'd take those two numbers and divide. I want to get a percentage out of that. So I'm doing 27 divided by 41 is about, if I round to the nearest tenth of a percent, that would be 65.9%. All right. We're looking for a number that's near 68. All right. So just going back to the instructions, well, really the rule itself, assuming a normal distribution, we can expect about 68% of the data to lie within one standard deviation of the mean. That's what we just figured out. We figured out what percent of data would lie within one standard deviation of the mean. All right. I made the little notation here just because it's often asked, what do you mean by about? What do you mean by approximate? All right. How far away is too far away?
How do you get
27 we got just by adding the 14 and the 13 together. All right. So if we're within 2 percentage points of 68, we're close enough. Now this is right on the bubble. So I'd look at this and say, well, this could go either way. Because if I round it, I'd round it to 66, which is within two percentage points of 68. All right. If I leave it unrounded, it's just far away enough to not be close enough. All right. So what we do is when we have a borderline case like this, we just move on to the next one. If it satisfies, so this one's pretty close. If the other two are also pretty close, then we can conclude that this is close to being a normal distribution. All right. The thing about statistics is very rarely, it's actually an extremely rare occurrence that we would say something is exactly a particular value. Right? Most of the time it's roundabout, pretty close, not too far away. It follows the same distribution, things like that. We've hardly ever say something is. So this just kind of falls into that category. All right. So the 14.542, if we're going with the number line approach, I'll draw it. Like I said before, you don't have to draw it, but I'm gonna draw it. So let's say we're starting at 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Let me go a little bit further. All right, so 15, 16, 17, 18, and so on. All right, so 14.5 would be about right here, 542 I should say. 23 and change, about right here. We're looking at any numerical value that's in this interval. So we're starting really with 14 doesn't make the cut, but 15 does. All the way up to 23, 24 would be out. So any of these values are fair game. All right, so all we're going to do is go to our list and see how many of each of these numbers there are. Well, there aren't any 15s. Actually, there's no odd numbers to begin with in my X list. 16 is in the highlighted area. 18, 20, 22, but not 24. All right. So I have a total of 4 different types of values. The 16s, the 18s, the 20s, and 22s. But the 16 occurs 7 times. The 18 occurs 14 times. 20 occurs 13 times, and 22 occurs 5 times. I need those counts. So in this interval, I have 39 values. And there's 41 values in the set. So we run the numbers. 39 out of 41. Well, if I round it to the nearest percent, it would be 95%. So that's pretty spot on. Even if I don't round it, it's 95.1%. All right, so that's kind of confirming what we thought with that first interval. That first interval was around 66%, pretty close to 68, but not quite. This one is pretty spot on. It's right at 95%. If the last one is right around 99.7%, then I would say that this is close to being a normal distribution. Right? That last interval goes from a little bit over 12 to a little bit over 25. Well, that's all the values. There is no value that's outside of this interval. So I don't need a number line for this. I can just say that it's 41 out of 41, which is 100%. All right? And that's because all values of X are between 12.398, and 25.260. All right. So this is close to being a normal distribution. All right. Now, it would be kind of fair for you to say there's got to be an easier way. All right. There is an easier, in terms of the computation way of doing it, but it requires you to know some stuff that we haven't covered yet. All right. So we'll get to it and we'll see. But this empirical rule is really the foundation of all probability stuff that we're going to get into. Right? So knowing that you're working with a normal distribution is going to be really important. Right? And so at this point, this is the technique that you would use to verify that that's the case. All right. Z-scores. So one example like that, and then a completely new topic. Yeah, just to confuse you as much as possible. No, that's not the case. I mentioned before that we'll do it by hand and then we'll do it on Excel. So one of the answers to the question of there's got to be an easier way, question mark, because that wasn't really a question, would be Excel. Excel or Google Sheets. All right, so I'm going to show you how you could do both of these topics using that in a couple minutes if we have time today. We'll see. But the z-score is really important concept too, because regardless of whether the distribution is normal, you can compare from data set to data set. But the thing is, those two data sets should have the same shape. Otherwise, it's an apples and oranges comparison. All right. So if I wanted to compare your math average through high school with somebody else's history or social studies average throughout high school, like how would I compare those two things? That's kind of a tall order. Like, what am I going to say? It was like, well, you had a 95 average in math and you only had a 92 average in social studies, right? But what if like everybody does well in math? My 95 doesn't mean a lot. Everybody gets a 95. I doubt that that's the case, but just go with it for a sec. But let's say social studies is really hard by comparison. Like a 92 in your social studies class may be a really, really good score. I did have an instance where I gave a math test. It's got to be like 15 years ago now. I gave a math test, and I wish I was making this up. Everybody except for one student got a 100 on the math test. It was about trig identities. If you're in Algebra 2, you'll get to that. All right. If not, then you may never see it. But it's not the most challenging concept. It's kind of like a puzzle, like a trig puzzle. Like once you understand all the rules, it's pretty easy to do. All right. So everybody in the class got a 100. Except for one student who got a 90. So that student's like, yes, I got a 90. And then because, like students are who they are, hey, what'd you get? What'd you get? What'd you get? It didn't take her too long to figure out that she was the only one who didn't get 100. So that feeling of getting a 90 on a math test, which is usually like hey, I did all right, it just got stripped away from her. And I felt so bad. But that could be the case. So how do we account for that? We account for that by computing z-scores. All right. So where you sit relative to your class. All right. So let's say maybe you're not the best math student, but you're an ace when it comes to social studies. But you only have a 90 average in social studies, whereas in math you have a 95 average. It's like, but I'm better in social studies than I am in math. Somehow I have a higher average in math. Maybe the grading system is more favorable in math. So we do an apples to apples comparison by computing z-scores. So I gave basically the same example. Michael and Jane are in different math classes. I stuck with math. Michael got a 75 on his math test, so we'll label this Michael and Jane. All right, so his score was a 75. All right, Jane got a 73. All right, the mean score in Michael's class was 73 with a standard deviation of 7.2. In Jane's class, the mean was a 71 with a standard deviation of 6.3. All right, I don't know why I put a decimal point there. So in both cases, I mean, if you just look at, okay, what's the class average and what did I get? All right, I got a 75, the average was a 73. So I did 2 points better than the average, right? So I'm above average. But I would want to know how far above average, 2 points. But these are measured on two different scales based off the standard deviations. So in Michael's class, the scores were more spread out because the S is bigger. All right. So if they're more spread out, then it takes less effort to get a score that's above average. All right. Whereas if they're more compressed, it takes a lot more effort to get a score that's above average. All right. Because you're always getting pulled towards the mean. Right? The baseline is whatever the class average is. Right? Where you stand relative to that is dependent on what the standard deviation is. Right? So in the case of Michael, I'll say Z sub M for Michael and Z sub J for Jane. All right. I'll color code it. This is my green set, and this is my yellow set. What we want to do is we want to find the difference between the individual score. So 75 and the mean, which is 73, and divide by 7.2. All right. Now, don't worry about, you see in the formulas, you have the notation, the one with the Greek letters, the mu and the sigma. Don't worry about that until the next unit. All right. We'll talk about that then. It's just we're only focusing on samples at this point, so we would use this variation in the formula. All right. Although it wouldn't really work out much different, but just really an FYI. For Jane, 73 was her score, 71 was the class average, 6.3 is the standard deviation. All right, so I'm going to take the 75 minus 73, which is 2, and divide that by 7.2. I'm going to get a 0.278. About. All right. For the second computation, it's really 2 divided by 6.3. So I get about 0.317. All right. Now, when it comes to z-scores, you got to be thinking about really two ways to interpret. One is that bigger numbers are better, and the other would be the reverse of that. Smaller numbers are better. All right. I always give the analogy of golf scores versus basketball scores. When you're playing golf, you want the score to be as small as possible because your score is how many strokes it took for you to get the ball in the hole. If it took me only 2 strokes to get the ball in the hole and it took you 10, your shots probably weren't as good as mine. All right? So my lower score is better than your higher score. Whereas in basketball, really pretty much every other sport, the higher the number you get, the more points you earn, the better off you are. All right? So hockey, you score 5 goals versus the other team who only scored 1, you won the game. All right. So this is an instance more like basketball than like golf. All right. So the higher the number, the better off you are. All right. In the form of a number line, if I go out 3 places to the left of 0 and 3 places to the right, that's the standard. I would plot 0.278 somewhere around here. and I would plot 0.317. Not really sure. I do know it's to the right of it though, just a smidge. All right, so we have Michael here and Jane here. All right, so what we learned from this is that Jane performed better relative to her class. I wanted to go all caps there and I got caught in the middle. Relative to her class. All right. She didn't perform better on the test. She performed better relative to the other students that also took the same test than Mike did compared to all the students that took the test that he took. All right. So you can't just say that Jane performed better than Mike. That's not true. Jane performed better than Mike relative to her class. That's the important piece there. All right. That's how you compare two different data sets. Right? So let's say you play golf on a Tuesday and it's a beautiful day like it is today, but then you play again on Thursday and it's drizzling out, it's overcast, the wind is blowing. You're probably not going to do as well on Thursday. But how did you do compared to everybody else who played on Thursday? How did you do compared to everybody else that played on Tuesday? Those are the two numbers that you want to be comparing.